Hello, I'm Colin Phillips.
And I'm Colin Jung. In this module, we will motivate the idea of modelling real-world phenomena using sequences of numbers. These sequences of numbers are generated by difference equations and recurrence relations. We will introduce some important concepts and notations for these difference equations and recurrence relations by concentrating our attention on arithmetic sequences. We will also explain in detail the distinction between a recurrence relation and their solutions, and work through some examples.
Slide 1, Motivation. To help you understand where a recurrence relation can be used and what it means to solve a recurrence relation, let's start with a real-world practical example. Imagine if Colin and I start a club for people who want to learn about recurrence relations.
To start with, we have found 10 enthusiastic mathematicians who wish to join. After watching our videos go viral, there is a grand total of 3 extra people that want to join the club every week.
So let's give these things some names. Let's call the number of people initially in the club x0.
So the number of people in the club after 1 week is x subscript 1, which throughout this module we will call x1. And the number after another week is x2. And after another week it's x3. And so in general, the number of people in the club after n weeks is xn.
The terms x0, x1, x2 and so forth forms a sequence of numbers. Let's work out precisely what the terms are and thus see how the membership of our budding club is changing over the weeks.
Firstly, x0 is equal to 10, our starting membership. In the next week, there are the original 10 plus 3 extra. That is, x1 is equal to x0 plus 3, which is 10 plus 3, which is equal to 13.
After yet another week, there's another 3 new members for our club. That is, the number of members after 2 weeks is the total number after the first week plus another 3. Hence x2 is equal to x1 plus 3, which is 13 plus 3, which is equal to 16.
And after another week, there will be another 3 members. That is, x3 is equal to x2 plus 3, which is equal to 16 plus 3, which is 19, and so on. One way to summarize all of this is just to say that the number of club members in the next week is equal to the number of club members in the present week, plus another 3 members.
As an equation, we write this as xn plus 1 is equal to xn plus 3.
Slide 2. Recurrence relations.
In our example, precisely the same thing happens from 1 week to the next. That is, there is a recurring theme, that 3 extra members join our club each week.
And because this equation relates the number of members in the week after to the number of members in the present week, we call the equation a recurrence relation. This simple example demonstrates the most important feature of a recurrence relation. This recurrence relation expresses a term as a function of the term preceding it.
If we write down the number of members in our club each week, that is, we write down x0, x1, x2, x3, and so forth, then for this example, this will be 10 initial members, then 13 members after 1 week, then 16 after 2 weeks, then 19, then 21, 24, 27, and so forth. So our recurrence relation has generated a sequence of numbers, and for this particular recurrence relation we call this an arithmetic sequence because there is a common arithmetic difference of, in this case, 3 between adjacent terms.
Now, let's say we want to project what the number of members will be after 100 weeks. We could just keep generating the sequence by using the recurrence relation 100 times, but there may be a better way of solving this problem. It will make the discussion simpler if we return to calling the initial number of members x0. Thus, there are initially x0 members.
Now after 1 week, the membership increases by 3. So x1 is equal to x0 plus 3. Now after 2 weeks, the number of members x2 will equal the number of members after 1 week plus our extra 3 members for that week. That is, x2 is equal to x1 plus 3. And we already know that x1 is just x0 plus 3. So x2 is x0 plus 3, which is just x0 plus 3 times 2. Now using the same method, x3 is equal to x2 plus 3, which using our formula for x2 is equal to x0 plus 2 times 3 plus 3, which simplifies to x0 plus 3 times 3. There is a pattern emerging. To make it a little clearer, let's work out one more term. x4 is equal to x3 plus 3, and using our formula for x3, x4 is therefore equal to x0 plus 3 times 3 plus 3, which simplifies to x4 is equal to x0 plus 3 times 4. In summary, we know that the number of members increases by 3 every week. So after 1 week, there's the original membership plus 3. After 2 weeks, there's the original membership plus 2 lots of 3. After 3 weeks, there's the original membership plus 3 lots of extra members.
Just by observing this pattern, we know that after n weeks, there will be the original membership plus 3 lots of n extra members. Thus, the membership after n weeks, xn, is equal to the initial membership x0 plus 3 times n. We have thus worked out a formula for the general term of the sequence, which, importantly, is expressed in terms of the position n. So, back to our problem of working out the membership after 100 weeks. We no longer have to iterate the recurrence relation 100 times. Instead, we can substitute n is equal to 100 directly into this formula, and it'll tell us the answer immediately and efficiently. This idea motivates the crucial discussion of what it means to solve a recurrence relation. Let's now explore and formalize these concepts. Slide 3. The concept of a solution to a recurrence relation. Let's consider the 2 important formulae that we have talked about in the last slide. The first formula, xm plus 1 is equal to xm plus 3, tells us the number of club members in the next week is equal to the number of club members in the present week, plus another 3 members.
The second important formula that we derived is xn is equal to x0 plus 3 times n, which tells us the number of club members in a given week by just using the number of weeks that have passed. So to work out the club membership in, say, the 3rd week using the recurrence relation, we would need to find out the membership after the 2nd week, which requires the membership after the 1st week, which means we have to use the recurrence relation a total of 3 times.
To calculate the club membership after 100 weeks, we just substitute n is equal to 100 into our second equation, whereas if we had to use the first equation, we would have to use it to find the membership after 1 week from the original membership, then use it again to find the membership in the second week, and then use the same recurring formula another 98 times before obtaining the membership after 100 weeks. So it's easy to see that for this problem, the second formula is much easier to use than the first. For this reason, we give these two different formulae different names. Because we have to keep recursively using the first formula to find any club membership, we call this equation a recurrence relation.
However, the second formula allows us to find the membership in any given week by just using the initial membership and the number of weeks that have passed. Most importantly, we do not have to use the solution more than once to find the club membership in any given week. For this reason, we call this the solution to the recurrence relation. This contrasts to using the first formula, where we would need to calculate the club membership for every week beforehand. So because the second formula solves the problem of directly finding the membership in any given week, we call this a solution to the recurrence relation.
Slide 4. Generating sequences using recurrence relations. We have already seen the idea that a recurrence relation generates sequences of numbers. In this slide, we explore the idea that each recurrence relation actually generates many sequences of numbers. In our club example, we started with 10 members of our club. So the relevant sequence of numbers generated by the recurrence relation, xn plus 1 is equal to xn plus 3, started with 10 as the initial term.
Let's consider the same recurrence relation, but drop the condition that we have to start with 10 members. That is, our initial term x0 can be anything. Thus, the recurrence relation xn plus 1 is equal to xn plus 3 can generate many sequences of numbers, depending on x0. For example, if x0 is equal to 1, we generate the sequence 1, 4, 7, 10, 13, and so on. If x0 is equal to negative 10, the same recurrence relation can be used to generate a very different looking sequence, minus 10, minus 7, minus 4, etc. If we start at 98, again exactly the same recurrence relation generates a very different looking sequence again.
If we start with the initial term of 10, then the sequence corresponds to our early example of the modelling enthusiast club. In fact, this recurrence relation simply generates all the arithmetic progressions with a common difference of 3. There are an infinite number of such sequences, depending on the initial term. Above, we have listed just 4 of the infinite number of sequences that can be generated using this recurrence relation. We write down the most general sequence for this recurrence relation by calling the arbitrary first term x0. This sequence will therefore be x0, x0 plus 3, x0 plus 3 times 2, x0 plus 3 times 3, x0 plus 3 times 4, and so on, with the general term being given by x0 plus 3n.
So from this we can see that the recurrence relation can generate an infinite number of sequences depending on the initial term x0, which is again completely arbitrary.
Slide 5. General and particular solutions. The formula xn is equal to x0 plus 3n is called the general solution of the recurrence relation. xn plus 1 is equal to xn plus 3.
For each x0 that we use, we obtain a different sequence of numbers. Every one of these sequences satisfies the recurrence relation. In fact, the solution xn is equal to x0 plus 3n will produce every single sequence that satisfies the recurrence relation, which is every single arithmetic progression with common difference of 3. Because we can generate every single sequence that satisfies the recurrence relation using this equation, we call it the general solution.
For each different value of x0, we can generate a different arithmetic progression. In this sense, the starting value x0 is arbitrary. For this reason, we call x0 the arbitrary constant of the general solution. In general, it's important to note that every general solution will include at least one arbitrary constant. It is also important to note that even though the arbitrary constant here is the initial value x0, this is not the case for the general solution of every other recurrence relation.
The most important point to notice about the equation xn is equal to x0 plus 3n is that it allows us to calculate any term in the sequence by knowing the position of that term n and one past term, x0, although it doesn't always have to be x0. For example, we can calculate the 100th term without having to calculate every one of the terms beforehand. This contrasts to using the recurrence relation to calculate the 100th term, where we would have to calculate every single term along the way. The equation xn is equal to x0 plus 3n can save us a lot of work by giving us the nth term directly. For this reason, we call this formula a solution to the recurrence relation.
We have seen that the recurrence relation, xn plus 1, is equal to xn plus 3, which has the general solution, xn is equal to x0 plus 3n, can generate an infinite number of arithmetic progressions, depending on the arbitrary constant x0, which, for this recurrence relation, represents the starting value of the sequence.
If x0 is known to be a particular value such as 10 initial members, then using x0 equals 10 in the general solution gives us a more specific formula. xn is equal to 10 plus 3n. This formula is still a solution because it allows us to find any term given n, but it's now a particular solution because it corresponds to just one particular sequence, in this case starting at 10.
So, in summary, xn equals 10 plus 3n is a particular solution because it corresponds to just one particular sequence, and it is still a solution to the recurrence relation because it allows us to find any term xn in that sequence by just specifying n. Slide 6. Recurrence relation versus its solutions. Both a recurrence relation and its solution can be used to do similar things. For instance, generating an entire sequence.
To best illustrate how they work differently, let's focus our attention on calculating just one term far along the sequence, say x100, using both the recurrence relation and its solution. We calculate x1 by substituting x0 into the recurrence relation, and then calculate x2 by substituting the x1 that we just found back into the recurrence relation. And then by iterating the recurrence relation over and over again, here we generate the terms x3, x4, x5, and so on. So to calculate x100, we would have to use the recurrence relation all of 100 times.
We see that using the recurrence relation to calculate a given term in the sequence means that we have to calculate every term before that. This is potentially a disadvantage and can amount to a lot of work if the term is far along the sequence. We should know that even though the solution can save a lot of work for calculating terms far along the sequence, if we just want to calculate the first few terms, it may be easier to just use the recurrence relation in this instance.
Now this is very different to using the solution to calculate any term in the sequence. For example, to calculate the 100th term using the solution, we just use the first term x0 and the position of the 100th term, that is, n is equal to 100. And very importantly, we don't have to calculate any of the intervening terms, x1 to x99. This can save a lot of work. In summary, this solution is different to the recurrence relation because it can be used to calculate a term xn at any position n in the sequence by just using n and the past term x0.
Slide 7. Recurrence relation versus its solutions continued. In the example above, the recurrence relation used xn to calculate xn plus 1. That is, the recurrence relation uses the previous term to calculate the current term.
To further explain the difference between a recurrence relation and its solution, let's consider a recurrence relation that uses the previous term and the term before that to calculate the current term. Let's consider xn plus 2 is equal to xn plus 1 plus xn.
It turns out the solution to this recurrence relation is the following. The solution looks complicated, and we will learn how to find this solution in a later module. For the moment, however, we will just use the solution to help explain how the recurrence relation and solution differ in calculating a term in the sequence.
Note that this is the general solution to the recurrence relation, and it involves two arbitrary constants a and b instead of just one, as in the last example. Let's now consider two specific sequences arising from this recurrence relation. For our first example, if x0 is 1 and x1 is 2, then using the recurrence relation, x2 is the sum of the previous term x1 and the term before that x0. That is, x2 is equal to x1 plus x0, which is equal to 2 plus 1, which is equal to 3. To calculate the next number, we add up the last two. So x3 is equal to 3 plus 2 is equal to 5. And then the next term is 5 plus 3 is equal to 8, and so on. So here, just as in the last example, if we calculate the 100th term using this method, we would have to use the recurrence relation all of, in this case, 99 times. Now consider the general solution to the problem. To find the particular solution for this equation, we would have to find the values of the arbitrary constants a and b. To do this, we would use x0 is equal to 1 and x1 is equal to 2.
We will talk about the details of this in a later module, and with some work, it turns out that a is equal to root 5 plus 3 all over 2 root 5, and b is equal to root 5 minus 3 all over 2 root 5. Don't worry about how we found these for the moment. Now, Because the arbitrary constants have been evaluated, this is then a particular solution.
Now again and importantly, the solution is different to the recurrence relation because we can calculate any term in any position by substituting n into the particular solution. For instance, to calculate x100, we substitute n is equal to 100 into the particular solution. Which here would give us a very large number. Even though this is a number too large for a handheld calculator and may need a specialist program from the web, it is much quicker than using the recurrence relation, especially as n gets larger. Importantly, there is no longer the need to generate every single intervening term before x100.
Let's look at one more sequence by choosing two different initial values, x0 and x1.
This time let's use the same recurrence relation but choose both x0 and x1 to be 1. Then using the recurrence relation, x2 will be x1 plus x0, which is 2. x3 will be x2 plus x1, that is 2 plus 1, which is 3. And x4 will be 3 plus 2, which is 5, and so on.
Now, you may recognize this sequence as the well-known Fibonacci sequence.
Again, to find the particular solution, we have to evaluate the arbitrary constants a and b. This time, a and b turn out to be the following constants, giving us the following particular solution. Just as in the previous example, don't worry about these details. We will explain how to evaluate the arbitrary constants in a later module.
Let's observe a couple of points from the last few examples and summarize. Firstly, we have seen that exactly the same recurrence relation can produce quite different sequences and hence particular solutions.
Secondly, when we use the two previous terms in our recurrence relation to calculate the current term, we get two arbitrary constants in the general solution, say a and b.
Thirdly, for all of these examples, it is much more convenient to use the particular solution rather than the recurrence relation to calculate terms for large n, that is, terms far along the sequence. However, in general, if you do not know how to solve a recurrence relation, or if you are only looking for terms with small n, it may be more efficient to just use the recurrence relation. Slide 8. Some notation and terminology. We have seen in this module how a simple recurrence relation can be used to model the membership of a club where the recurrence relation generated a discrete sequence of numbers that describe the numbers of members as the weeks went on.
A different method of modelling how quantities change is to use differential equations, or DEs. Some of you have already seen differential equations in your studies. In contrast to this, recurrence relations that we are considering here model discrete quantities. That is, quantities where measurements are taken at regular intervals. After differential equations, difference equations are the second most common method for modelling natural and physical phenomena. Some of our students may recognise that differential equations are used to model continuously varying phenomena.
Now, going back to our club membership model, imagine that D extra people join our club each week. The recurrence relation for this would be xm plus 1 equals xm plus D. But this is not the only way of writing down this relationship. For instance, if we subtract xn from both sides, this gives xn plus 1 minus xn is equal to D. Now, in this form, the left-hand side represents the difference between the club membership on one week and the club membership the week before. For this reason, this special form of the recurrence relation is called a difference equation. Now, for this specific example, the difference is a constant d. And because the left-hand side is the difference between successive terms and the right-hand side is a constant, we call this a constant absolute difference equation.
Now, we can use the equation on the left specifically to calculate a term from, in this case, the previous term. However, the equation on the right is written to express the difference between two consecutive terms. For this reason, the equation on the left is often referred to as a recurrence relation, and the one on the right can also be referred to as a difference equation. In some courses, however, the terms recurrence relation and difference equation are used interchangeably. In this model, to make things a little simpler, we keep the equations in the first form and just use the term recurrence relation.
As we've seen above, we can rearrange a recurrence relation to be in the form of a difference equation. And in general, there are many different ways of rearranging a recurrence relation to give different looking equations. But even more than this, there are other quite different looking recurrence relations that will produce exactly the same sequence of numbers.
For example, consider the following three recurrence relations. Even though all three equations look different, they share a very important property, which is that they all generate the same family of sequences. In this respect, we say that all three recurrence relations effectively represent the same model.
Now, to see how these three equations are related, consider this recurrence relation and replace n by n plus 1 everywhere, so that xn plus 1 on the left-hand side becomes xn plus 1 plus 1, and xn on the right-hand side becomes xn plus 1. The subscripts then simplify, and we get the following equivalent equation.
To summarize, replacing n by n plus 1 throughout the original equation produced the new equation. A simpler way to remember this process is to just add 1 to all the subscripts. That is, we have shifted all the indices up by 1.
In a similar fashion, if we once again start with the middle equation, then if we replace n by n minus 1 everywhere, then xn plus 1 on the left-hand side becomes xn minus 1 plus 1, and xn on the right-hand side becomes xn minus 1. Simplifying the subscripts then gets us the following equivalent equation.
That is, here replacing n by n minus 1 throughout the original equation produces the new equation. Or you could think of it as just subtracting 1 off of all of the subscripts, so that we have effectively shifted all the indices down by 1. In summary, adding or subtracting an integer to all of the subscripts in a recurrence relation does not change the model. Even though this process will produce a different looking recurrence relation, they will generate the same family of sequences. By adding or subtracting an integer to all of the subscripts, we can determine which recurrence relations can produce the same sequences of numbers and thus describe the same model. To see if recurrence relations are equivalent, we need to ask, can we add or subtract the same number from every subscript to turn one recurrence relation into the other?
Another way to understand this phenomenon is to notice that all three equations are giving us the same information. They are all saying that to obtain the next term in the sequence, we use the present term and simply add d. Thus, it should come as no surprise that all three recurrence relations generate the same family of sequences, and therefore effectively represent the same model. Finally, we note that as a matter of terminology, other letters are sometimes used in place of n for the subscript. Other common choices are, for instance, I or M. Slide 9. Order of a recurrence relation. For our book club example, where the membership of the club in 1 week is equal to the membership the week before plus 3 new members. To calculate the membership in any week, we needed to use the membership just 1 week before. We say that the order of this recurrence relation is 1.
More generally, consider any sequence generated by a recurrence relation. Then the number of positions between the term with the highest subscript and the position of the term with the lowest subscript represents the order. That is, the order is the gap or difference between the highest and lowest subscript which occurs in the equation.
Thus, to calculate the order of a recurrence relation, we locate the largest subscript and then subtract away the lowest subscript. Intuitively, the order of a recurrence relation tells you how far back in the sequence you would have to traverse in order to generate each term. An order 1 recurrence relation relates immediately adjacent terms. An order 2 equation relates terms up to 2 positions apart, which may include terms 1 position apart. Let's study some examples.
So for our book club example, the highest subscript is n plus 1, the lowest subscript is n, so their difference is n plus 1 minus n, which is 1, thus verifying the order of our book club equation to be 1. For this example, the highest subscript is now n plus 2, the lowest subscript is n plus 1. Now the order is the highest subscript minus the lowest subscript. Here, that is n plus 2 minus n plus 1, which is 1. Thus, the order is again 1.
Even though the subscripts in the second example look different to the subscripts in the first example, the order is exactly the same. Just as importantly, it doesn't matter how big the subscripts are. All that matters in calculating the order is the difference between the largest and smallest subscripts. Remember that both of these recurrence relations are simply saying, to get to the next term, we add 3 to the previous term, and as such, will generate the same family of sequences. Thus, it should come as no surprise that both are the same order 1.
To emphasize this point, for this example, the largest subscript is n plus 145. The lowest subscript is n plus 144. Thus the highest subscript minus the lowest subscript is n plus 145 minus n plus 144, which is again 1.
The one distinguishing feature of all order 1 recurrence relations is that we use only the previous term to calculate the current term.
For this example, the largest subscript is n minus 3. The smallest subscript is n minus 4. Thus the order is n minus 3 minus n minus 4, which simplifies to 1. Thus this recurrence relation is also first order. For this example, the largest subscript is n plus 2, the smallest subscript is n, thus the order is n plus 2 minus n, which is 2. Thus this recurrence relation is order 2 or second order.
For this example, we not only use the previous term to calculate the current term, but also the term before that too. That is, we use the term 2 positions before the current term. If we imagine the terms written out as a sequence of numbers, to work out the current term, we have to use the term 2 positions prior. Thus, the number of positions between the term with the highest subscript and the term with the lowest is 2.
Here, the largest subscript is n minus 6, the smaller subscript is n minus 8. The gap between the largest and smallest subscripts is thus n minus 6 minus n minus 8, which is 2. Thus we have another second order model. In our final example, the largest subscript is n plus 5 and the smallest is n. So the order is n plus 5 minus n, which is 5. Thus this recurrence relation is order 5 or fifth order.
It's important to observe that in this recurrence relation, to calculate the current term, we're using the term previous and the one before that, along with the term 5 positions earlier in our sequence. So even though we're only using 3 previous terms, the number of positions between the term with the highest subscript and the term with the lowest subscript is 5.
From this example, we can see that the order of a recurrence relation depends on how many positions prior in the sequence we need to backtrack through in order to compute the present term. It's not just determined by how many previous terms that we use.
In general, for any recurrence relation, the order is not determined by the size of an individual subscript, nor the number of previous terms we use. The order of a recurrence relation is determined by how many positions in the sequence we need to backtrack through in order to calculate the present term.
All of these ideas are important, but if you simply remember that the order is just the difference between the highest and lowest subscripts, then you can't go wrong. Slide 10, worked example. To consolidate what we've learnt so far, let's solve a couple of constant absolute difference recurrence relations. These examples will be presented in a double column format where the left-hand column corresponds to the basic theory and the right-hand column corresponds to the theory applied to our example.
For our first example, we want to find the particular solution to the recurrence relation xn plus 1 minus xn minus 7 is equal to 0, given the condition that x0 is equal to 19.
Our strategy here is to first find the general solution of the recurrence relation.
We then use the given condition to find the arbitrary constant and then the particular solution. Our first step is to rearrange the recurrence relation into a standard form. Here, for this recurrence relation, that means we must rearrange the recurrence relation so that the term with the highest subscript, that is, xn plus 1, is on its own on the left-hand side.
For our example, this means we add xn and 7 to both sides of the equation, giving xn plus 1 is equal to xn plus 7.
So here, we want to find sequences that satisfies the property that the next term is always the present term plus 7. This recurrence relation therefore generates a family of arithmetic progressions, all with common difference 7.
So for this example, the common difference d is 7.
In step 3, we write down our general solution. That is, we want to write down a general formula that expresses a given term xn only in terms of n, its position in the sequence.
For our example, this is xn is equal to the initial term x0 plus 7 times n.
Recall that general solutions always contain arbitrary constants. Here, the arbitrary constant is x0, which can be any real number. Now that we've found the general solution, we can proceed to find the particular solution, subject to the given condition. What is the given condition here?
For our example, it's x0 is equal to 19. In other words, our initial term in the sequence should be 19. Our particular solution is therefore xn is equal to 19 plus 7n.
In summary, we have found a formula called a particular solution that will allow us to find any xn by just using n. This allows us to find xn without having to generate the whole sequence. For instance, when n is equal to 100, x100 will be 19 plus 7 times 100, which is 719. If we wanted to find x100 using the recurrence relation, we would have to generate every single term in the sequence before x100.
Slide 11, final example.
For our second and final example, we want to find the particular solution to the recurrence relation. 3 times xn plus 1 is equal to 3 times xn minus 15, given the condition that x0 is equal to 26.
As in the previous example, we will first find the general solution of the recurrence relation before evaluating the constant to find the particular solution.
Our first step is to rearrange the recurrence relation into a standard form, where the next term, xn plus 1, is on its own on the left-hand side.
Here, this means we divide both sides by 3, giving xn plus 1 is equal to xn minus 5.
So here, we want to find sequences where the next term is always the current term minus 5. This recurrence relation therefore generates a family of arithmetic progressions, all with the common difference negative 5.
So for this example, the common difference d is negative 5.
We then write down our general solution. That is, we want to write down a general formula that expresses a given term xn only in terms of n, its position in the sequence.
So for our example, this is xn is equal to the initial term x0 minus 5 times n, where x0 is an arbitrary constant.
Now that we've found the general solution, we can proceed to find the particular solution, subject to the given condition.
Here the condition is x0 is equal to 26. In other words, our initial term in the sequence should be 26. In particular, the solution is therefore xn is equal to 26 minus 5n.
This particular solution allows us to find any xn by just using n. This allows us to find xn without having to calculate any of the previous terms beforehand. This module describes how to solve a difference equation or recurrence relation that generates an arithmetic sequence.
More than this, we also explain the general ideas of a difference equation, a recurrence relation, how a solution to a recurrence relation differs from the recurrence relation itself, the order of a recurrence relation, and how the different notations work.
All of these concepts are important for understanding other recurrence relations in general.